In this video, we'll solve problem 9.86 from the book Thermodynamics in Engineering Approach, Cengel 9th edition. Here is the statement of the problem 9.86. A gas turbine power plant operates on the simple Brayton cycle with air as the working fluid and delivers 32 megawatt of power. The minimum and maximum temperatures in the cycle are 310 and 900 Kelvin, and the pressures of air at the compressor exit at 8 times the value at the compressor inlet, assuming an isentropic efficiency of 80% for the compressor and 86% for the turbine. Determine the mass flow rate of air through the cycle. Account for the variation of specific heats with temperature. Before taking the data from the statement, let me draw first the TS and PV diagram of the Brayton cycles. Ideal Brayton cycle remembers when the isentropic efficiency of the turbine and compressor is 100%. Before making the TS diagram of the Brayton cycle, let me explain the schematic diagram of the Brayton cycle. 1 to 2 is isentropic compressions, 2 to 3 is constant pressure heat additions process, then 3 to 4 is isentropic expansion in the turbine. The compressor and turbine are connected to a common shaft that will give you the net work output, and the net work output is the difference of work input during compressors minus work output during the turbine, and then heat rejection at a constant pressures to the environment. Now come toward the TS diagram of the ideal Brayton cycle. Now we will start from 1 to 2, that is isentropic compressions. 1 to 2 is isentropic compression, then 2 to 3 is constant pressure heat addition process, then 3 to 4 is again isentropic expansion in the turbine, and then finally heat rejection at a constant pressures to the surrounding. Remember, this is a TS diagram. The entropy here S3 is equal to S4 and S1 is equal to S2. This is the ideal Brayton cycle. Remember, when the efficiency of the turbine and compressor is 100%, then the ideal Brayton cycle will look like this. If the efficiency of the compressor decreases from 100%, then the temperatures after compressions is slightly, you will observe, higher than ideal one. This is, let's say, the actual temperatures T2. This is the ideal temperature T2S when the compressor is working at 100% efficiency. Similarly, when the turbine is 100% efficient, the entropy at the inlet and outlet will be the same, and it means that the T4S value will be lower as compared to the actual one. Since the turbine efficiency is 86%, that's why it will give you less work output, and the output temperatures of the gases after the turbine will be as compared to the ideal one. So here is T4, here the temperature is T4S for ideal case, and here the temperature is T4 for actual case. For actual case, T4 value is greater than T4S. To get the maximum power output from the turbine, our concern is to lower the T4 value to get you the maximum power. I hope you understand the TS diagram. The maximum cycle temperatures you will observe is at T3, and the lower temperatures at the inlet of the compression, that is T1. Similarly, if I draw the PV diagram of the Brayton cycle, first is isentropic compression. Pressure increases from P1 to P2, then constant pressure heat addition process. Here it is, that is 2 to 3. Then 3 to 4 is isentropic expansion in the turbine, that will give you the work out. Here you will provide the work input in order to run the compressor, and then 4 to 1 is constant pressure heat rejection process, is Q out. Here the volume is V4, here the volume is V1. This is ideal PV diagram of the Brayton cycle when the entropy of the turbine and compressor is 100. If you understand it's the concept of the Brayton cycle, TS and PV diagram, then come toward the statement, what kind of data that is provided in the statement, then we'll move toward its solutions. The net power that is produced is 32 megawatt. Of 32 megawatt multiplied with 1000, it will convert into kilowatt. The minimum temperature is T1, that is 310 Kelvin, and the maximum cycle temperature is T3. And also it said the pressures of air at the compressor exit at 8 times the value at the pressure inlet, means to say that the pressure ratio P2 divided by P1 is equal to 8. Now next it said compressor is 80% isentropic and turbine is 0.86. We need to calculate the mass flow rate of air to the cycle. Now consider the process 1 to 2, that is isentropic compression. So I can say that T2S divided by T1 is equal to P2 divided by P1 gamma minus 1 divided by gamma. After solve this on calculators, you will get the T2S value, and it is 561.5 Kelvin. Also, we know that the isentropic efficiency of the compressor is equal to isentropic work input divided by actual work input, and this isentropic work input is equal to Cp change in T2S minus T1 divided by T2 minus T1. This T2 is the actual temperatures after compressions when it multiply with the compressor isentropic efficiency. So this Cp will cut out with this Cp, and you will get the compressor efficiency of the compressor will equal to T2S minus T1 divided by T2 minus T1. I am rearranging this equation for the T2. After solving this on calculators, you will get the T2 value. Now the actual work input required in order to run the compressor is equal to Cp T2 minus T1. Cp value is 1.005. T2 is, after solving this on calculators, you will get the work input required to run the compressor, that is 316 kJ per kg. Consider the process 3 to 4, that is isentropic expansion. T4S divided by T3 is equal to P4 divided by P3 into, remember this P4 divided by P3, so here it is P4 divided by P3, so it means it is the reciprocals of the pressure ratio. So here I can write like this. After solving this on calculators, you will get the T4S value, and it is 496.8 Kelvin. Also, the turbine isentropic efficiency is equal to the actual work output divided by isentropic work output. Also, this in terms of temperatures is equal to T3 minus T4 divided by T3 minus T4S. Further, I can also write like this: T3 minus T4 is equal to efficiency of the turbine into T3 minus T4S. Now just simply enter the values. So solve this all terms, and in terms of this we can write 346.76, and finally I can write like this: T4 is equal to 553.3 Kelvin. Now the actual work output by the turbine when it is 86% isentropic. Solve this on calculators, and it will give you the work output, that is 348.5 kJ per kg. Now the net work output per kg is equal to actual work out by the turbine when it is 86% isentropic minus work input that is required to run the compressors when it is 80% isentropic. And the network output 32.5 kJ per kg. We need to calculate the mass flow rate of the air, and the network output per kg multiplied with the mass flow rate will give you the power produced. It is 32.5. This mass flow rate we need to calculate, and is given in the statement, that is 32,000 kilowatt. Divide both sides with 32.5. When you solve this on calculators, it will give you the mass flow rate of the air, that is 984.6 kg per second. And this is our final answer. I hope you understand. If still there any confusion, you can ask in the comment section. Please subscribe my channel if you haven't subscribed. Thank you so much.